welcome back to your favorite intermediate algebra course. Good to see you. Today we're going to talk about probability. So this is just a little introduction to this section here. Probability is any number between 0 and 1 that indicates the likelihood of an event will occur. For instance, the old classic, what's the probability of flipping a heads? I have a 1 in 2 chance, or 0.5. 0.5 is between 0 and 1. I have a 50% chance that theoretically, that I will flip a heads. Okay, if I'm flipping a coin, what's the probability that I flip a king? Well, 0. I have no chance because it's either heads or tails that I'm going to flip. What's the likelihood that I'm going to flip a heads or a tails on one flip? Well, that's 100% guaranteed. Okay, so it ranges between 0 and 1. Now you have experimental and you have theoretical probability. Experimental is when you actually perform the experiment and what you get. So for example, move this down a little bit. Let's say we flip a coin, if your coin 10 times, and let's say we get and we're trying to figure out what's the probability of flipping a heads. And when we do it 10 times, we get heads, heads, tails, heads, 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 tails, tails, heads. How many is that? 3, 5. And one more heads, we'll say. Okay, so this is what happens. And you notice what happens here is we got 1, 2, 3, 4, 5, 6, 7 heads. It's actually what happened out of 10 total tosses of the coin. So experimentally, we have a 0.7 probability here. So this is our experimental probability. Whereas theoretically, if we were to do it 10 times, we're expecting half of the time, or 5 out of 10, we're expecting a 1 in 2 chance, theoretically, to get a tails. I'm sorry, a heads. Gosh, probability of getting a heads. All right, so theoretically, can be different than experimental, and obviously as you do it more and more times, experimentally will approach your experimental probability will approach your theoretical probability. Okay, so let's go back up to here, and this is just showing that our theoretical probability of an event, the probability of event A occurring is number of outcomes in A, so kind of like the successes, if you will. How many times did you actually get a heads out of total number of outcomes? So how many total times did you flip the coin? Okay, and that. All right, let's do rolling a die. So the results of a six-sided die are shown in this table. Okay, so somebody rolled it 120 times. Use the table to find the experimental and theoretical probability of each event. And I forgot to tell you, let's see here. Let's say rolling a 6. Okay, well, theoretically, if you were to roll a 6, just the number 6, you have a 1 in 6 chance, right? So if you're to do it, 1 in 6, or 0.167, 0.167. Okay, so that's theoretically what you would expect. Now experimentally is shown above in this table. When somebody actually rolled this 120 times, it shows how many times did they get a 6. So let's look. It looks like 26 times. 26 times, that's a success, right? 26 times we rolled a 6, and we rolled it 120 times total. Okay, so 0.217 was our experimental probability. Okay, so our experimental probability was actually higher than the expected theoretical probability of 0.167, right? Of course, if we have a 1 in 6 chance, if you're theoretically speaking, if you're to do 120 times, you're theoretically you're going to get 20 out of 120 is 0.167. That's 1 in 6. Okay, so we're expecting to get 20 rather than 26, which experimentally is what occurred there. All right, let's do some playing cards here. So we have the standard deck of 52 playing cards. We got the 4 suits here, 13 different cards in each suit. Find the probability of drawing a king. Okay. So if you notice there, how many kings do we have? Well, we got the king of clubs, we got the king of diamonds, we got the king of hearts, we got the king of spades. So for this part A, move this down a little bit. For part A, the probability of getting a king, how many kings? I got 4 out of 52. So a 1 in 13 is my probability, or 0.077. 0.077. Okay, 7.7%. Part B, let's do probability of drawing a heart, any heart card. You say, well, how many hearts are there? Well, ace, 2, 3, 4, 5, 6, 7, 8, 9, 10. And then you got your jack, queen, king, right? You see all those hearts there? How many of them are there? Well, there's 13 in each suit. So 13 out of 52, or 1 in 4, or 0.25. Okay, so there's our probability of drawing a heart. Part C, probability of drawing a card less than or equal to 7. Okay, so let's go back up here. How many of these are less than or equal to 7? So I got 7, 6, 5, 4, 3, 2, and the ace, right? So 1, 2, 3, 4, 5, 6, 7 in each suit. I have 7 of those in each suit. Of course, there's 4 suits, right? Out of 52, right? 13 times 4. So we got 28 out of 52. Of course, that was 7 out of 13, which I just showed you right there. You could have canceled those. Okay, so we have a 7 and 13 probability of drawing a card. 0.538. Drawing a card that's less than or equal to 7. Okay. And these are all theoretical probabilities there. All right, so let's do some probabilities with permutations or combinations here. There's 20 students in your gym class. Your teacher divides the class into 2 equal softball teams. Okay, so you got a team of 10, right? Team of 10. All right, your team draws names one by one to determine the batting order. What's the probability one of the 7 freshmen, so you have 7 freshmen on the team, will be chosen first? Okay, so we're going to consider that the 7 is within that team of 10. Okay. So what's the probability one of the 7 will be chosen first? Probability 1 of the 7 will be chosen first. Well, how many different ways can you choose a freshman? You know, your success, if you will. You have 7 choose 1 ways. 7 choose 1, we're choosing 1 freshman, right? That's the probability, or I'm sorry, that's the probability that an event occurs, right, on the top there. And total ways to do it is 10, and I'm choosing 1, right? 10 on a team, and I'm choosing 1. Okay, so you punch that in, 7 choose 1 over 10 choose 1. And you got 7 over 10, or 0.7. Okay, so the probability of choosing a freshman is 70%, 0.7. So you can use your permutations and combinations probability as well. Okay. All right, how about another experimental probability? So here's the first exam grades of students in a biology class. They're shown in the bar graph there. Find the probability that a randomly chosen student in this biology class received a B or better. Probability of a B or better, right? So an A or a B. Well, how many students got a B or better? It looks like the B's, looks like there's what, 11 here? How many A's there? Looks like we got 5. Okay, so 11 B's, 5 A's, that's the successes, if you will. Divide by how many total students was there. So I gotta add up all my F's. It looks like there's no D's, is there? So F's, C's, B's, and A's. It looks like F's there was 1, C's there was 9. So it looks like total, looks like we got 16 over, what's that, 26? So 16 over 26 ends up being 0.615. 0.615. That's the probability that a randomly chosen student in this class got a B or better on that exam. All right, so let's look at this problem here. This is an example of like a geometric probability problem. We're going to use area to find probability. You throw a dart at the board shown. Your dart's equally likely to hit any point inside the square board. Are you more likely to get 15 points or 10 points? And of course, this is, like I say, it's equally likely to hit the board. So we're taking skill out of this, if you will. So let's figure out first of all the probability of getting the 15 points here. Okay, so if you look at the 15-point area here, you see it's all shaded in gray, right? Problem is I don't want to include the 20-point area. Okay, so I need to figure out the probability of the green part, but then I want to subtract out the 20-point area, and I'll be left with the gray shaded region. Okay, that's the area of the 15-point. Okay, so you remember area is base times height, right? So the area of the green region, you notice it's 8 across, and this is square, so 8 times 8. Okay, that's the green area. And I got to subtract out the 20-point region, so the red area, which is 4 base height 4. Okay, so we got this 64 minus 16. What's that? I'm forgetting here. Yeah, 48. That's right. 48. Okay. So we got 48 is the area on the top. So that's the 15-point area. Let me erase this. Okay. Out of the entire, erase that there. Out of the total area of the whole thing, okay, which is be 12 squared. Okay, 12 times 12. Area, the entire thing, 12 times 12. So 144. Okay. So 48 out of 144. Looks like we got 0.3 repeated. Okay, so 1 and 3. 0.3 repeated. All right. Now let's do the probability of the 10-point area. Probability of the 10 points. Okay. Now you see the 10 points is that white stripe on the outside, right? Like this is all the 10-point, if you will, right? So what we're going to have to do is we're going to have to take the area of the whole thing, right? And we're going to have to subtract out this inner area right in here. The shaded, both the 15 and the 20-point areas. Okay, so the red minus the black there is going to leave us with the 10-point region. Okay, so let's go. The red part is 12 base times height, right? And I'm going to subtract out the black region, which is base times height, 8 squared, right? So we got 144 minus 64 there. Let's see, what's that? 80. Okay, so that's the 10-point region area is 80. So that, again, that stripe on the outside is what we just figured out by taking the big red area minus the black area. Okay. All right. And it's out of the entire dartboard, which is base 12 times height 12, so 144. So 80 out of 144 ends up giving you 0.556. Okay, so back to the question, are you more likely to get 15 points or 10 points? Well, which one's a better probability, the 0.556 or 0.3? And you say, well, definitely the 0.556. More likely to get the 10 points. That's probably why it's worth less, right? So 10 points more likely is what's more likely. Okay, you guys make sure you bring questions to class. See you soon.